Now, once we come up with the solution state diagram, then it's pretty much methodical from that point. Okay, so what we do with this state diagram is construct a state table first. What this state table contains is basically a table representation of this state diagram, whatever the state transitions and switching and stuff like that. And we kind of avoid putting the reset state and that thing, like we just want to focus in this table on the main function. Okay, reset state from the diagram, it is clear, okay, it goes to A, that's fine. Okay, but we are mainly trying to capture in the state table as my state transitions. So one of the column, we start with the present state. If my state is A or B or C, then my next state and output columns, and that for these machines, since it has one input, and of course we are trying to be very particular about the reset, so we are assuming reset states zeros for all these table entries that we are trying to make here, and X will assume different values. So we have one column for the next state, another column for the output. Of course, like from the state diagram you can see, like one part is what the next state is going to be, another part is what's my output is going to be. Now it says, look at this, like from state A, if my present state is A and X is 0, output 0, next state A. That's what we are entering. Present state A, X 0, next state A, output 0, right? Then we are defining, if my present state is A, input 1, next state B, output 0. So that's what we are doing in the very first row, right? Present state A, X equal 1s, next state B, X equal 1, output 0. Okay. Similarly, from B, it's basically current state B. If it is 0, X is 0, output 0, next state A. Okay. Present state B, next state would be, if X is 0, next state would be A, and output would be 0. Now from B, if input is 1, output 0, next state C. So that's what we are encoding here. When B is, present state is B, X equals 1, my next state becomes C, and output is 0. So in this fashion, we complete this state table, come up with a state table. Okay. And now from this state table, I put a state assignment. Okay. So now instead of presenting the state as a letter A, B, C, D, I mark it with using like bits. Okay. So I have 4 state. So represent 4 things. We need log base 2 of 4 means 2 bits, right? Represent 4 states. We need 2 bits, log base 4, 2 bits. So I assign 2 bits to represent a state, and I assign like A is 0, 0, B is 0, 1, C is 1, 1, D is 1, 0. This is kind of, I would say, arbitrary choice. I chose a state transition in a fashion where only 1 bit changes from each other. You know that means what that means. This is I choose a gray code method of transition. From A to B, it becomes 1 bit change. B to C, it becomes 1 bit change. C to D, it becomes another 1 bit change. So that's what is my logic behind assignment. So you can assign it like 0, 0, 0, 1, 1, 0, 1, 1. Absolutely fine. In back of my mind, why I chose gray code, it may help to reduce circuit complexity, since we are dealing with, at each transition, we are dealing with 1 bit change instead of 2 bit change. So it may contribute to much simplified circuit. Okay, so but not a major impact, by the way. It is not a major impact on the circuit if you can do another state assignment. Not a major impact. It will be minor tweak here and there. That's fine. So we assign these combinations of bits, like 2 bits, to the different state, and just rewrote this previous state table which is written in later code for the state with those bit pattern code. So we come up with this, like all these bit pattern codes, like 00 is A. So wherever there was A in the whole table, I replace them with a 00. Wherever there is a B, I replace them with 01 in this table. Wherever there is C, I replaced with 11 in this table. And wherever there is a D, I replace with 10 in this table, and I come up with the state assigned state table. Okay, this is state assigned state table. Now from this state table, let's go and make a truth table. Okay, so how we do it? Now let's call first of all this presence, like the bits that represents the state. Like we kind of think, okay, thought that, okay, we'll use 2 bits to represent this 4th state. So each of this bit, let's call them a state variable. Okay, state variable A, T and BT. Means the subscript T is nothing. This is just a name to tell you that at this present iteration, at this present clock cycle, or at this present time, whatever way is you are comfortable to think of this temporal correlation, this AT is my current value of one of the bit, and BT is the current value of another bit. Like let's say the first bit of the state combination 00, first bit let's make it an AT, and second bit let's call it a BT. Okay, and I have another primary input X. So if my AT and BT 00 and X is 0, then my next state, okay, state variable AB at the next state, which is marked as AT plus 1 and BT plus 1. So you're kind of familiar with this concept, with this sequential circuit concept and sequential components, which we kind of talked about this, like on the flip-flop and latch truth table writing. Like remember that QT plus 1 notation, it's the same thing. Just we are calling it an AT/BT as a state variable, and the next state become, each of the bit become AT plus 1, BT plus 1. So since you see from the state table, my AT equals 0, BT equals 0, X equals 0 will results in AT plus 1 0, BT plus 1 0. Okay, that's what we place there, and Z is also 0. Similarly, we put a present state AT 0, BT 0, X 1, next state become AT plus 1 becomes 0, BT plus 1 become 1, right? 0, 1, next state. And then present state AT 0, BT 1, X 0, the next state AT plus 1 0, BT plus 1 0. Present state AT 0, BT 1, X 1, then my next state AT plus 1 is 1, BT plus 1 is 1, and so on and so forth. So that's how we translate the state table into the truth table, just marking them as this AT/BT as a variable. By the way, this is nothing, this AT/BT nothing to do with your state letter, like it is nothing to do with your this A, B, C, D. This is no relation. This is just an arbitrary naming. It happened to be AT/BT. I could have named it as a like an YT/ZT as well, or MT/NT. Like, so what I want to be make you clear that AT/BT is nothing to do with the state name here in this slide, A, B, C, D. Nothing to do with that. They are just independent. I just happen to name them this 2-bit variable as AT and BT. Okay, and they call it a state variable because we represent the state with these bits. All right, and we derive this whole truth table based on this state table transition, which includes my state variable's current values, next value of the state variable, and the output. depending on the current value of the state variable and the primary input. So from here we can well imagine this the SOP form of the each of this output variable, like which is this is one of my output, and BT plus 1 and AT plus 1, they are also this next state variable, there also becomes my output from this sequential circuit, right? So I basically call make an AT plus 1 is a sigma of 367. We know how to, from our truth table, how to make an SOP form. We all know that already from the previous Boolean algebra discussions. So here be careful, like some people actually mistakenly make it like 1 2 3 4 5 6 7 like that, but you need to consider the values of this bit pattern to make what this mean term index is. So it is really not strictly in order of the line, but it is basically your combination of these bits that determine what the mean term index would be, right? So we all understand from our, again, Boolean algebra 2 discussion on that. So be careful on this when you assign this mean term for the each row. That's one pitfall. That's usually we tend to forget and just, you know, assign this in a sequence 0 1 2 3 4 5 6 7, and all the circuit then is wrong basically from this point. Anyway, from the truth table we come up with the SOP form, and also note that the function name, like for the z, I just put this z as a function of AT, BT and X, and which is sigma 5, that's fine, a sigma m5, and AT plus 1 and BT plus 1, I choose the function name notation has to be D, like instead of F, that is the usual way, I just put as a DA and DB, okay? I'll tell you why, because this will clear up what my digital circuit would going to look like, okay? So this D in fact stands for my D flip-flop, okay? Remember the D flip-flop component from the last lecture, sequential like storage element, D flip-flop we talked about. So this is D flip-flop, okay? So instead of calling it a F, A or something like that, we just name it as a D. The function name is D of A, subscript A, and that's a function of AT, BT and X, and which is sigma M367, and BT plus 1 is DB, another D flip-flop equation, AT, BT, X, sigma 1357. So once we have it, then we solve these for AT plus 1, BT plus 1 and Z, optimize it through the K-map, and AT plus 1 and BT plus 1, these two equation is basically called a state equation, okay? And Z is your output equation. So we have two component in sequential circuit design when we are optimizing the equations. One part is the state equation, which basically gives you the Boolean function for the state change, and another is the output equation. So two part of it. So once we have this state equation and output equation, we can now make it map to the technology libraries, which has, like, let's say all the gates available, all type of gates. We just pick up things, whatever we need to do. If it had been some limited access, like let's say it doesn't have a D flip-flop, it has an other type of flip-flop, we need to adjust our circuit accordingly. Let's say it didn't have an AND gate or OR gate, let's say it had just a NAND gate, for example, then we know how to translate all the logic equations, especially using the De Morgan, into NAND only circuit. So we could have done that. But for our simplicity for this problem, let's assume we have all the logic gates that we need, whatever, right? So we have our state equation DA, ATBT or BTX, and db is x, and output equation as at bt bar and x. Okay, so what we'll do for these two term state equation, we place two flip-flop. Let's mark them A and B. So A is going to be your DA and B is going to be DB. What I mean by that, A is providing your AT, means the Q output is providing the value of the variable, state variable AT. Okay, and this B flip-flop, the Q output is providing the value of the BT. Okay, so, and that means my next state, which is like AT, the next AT plus 1, what is that? That is your AT and BT or BT and X, right? That is the whole equation we just came up with the K-map, right? So that is my AT plus 1, which is the input, which basically is the input of the D flip-flop, because upon the clock reach, it will, this state will reflect into Q, right? This logic will, D logic value at the D will reflect it on the Q side, right? So that's my state transition. Similar for the B, this D flip-flop marked as B, your BT plus 1 is your input at the D side. On the next clock, this logic will translate into Q. That means together, this D, A and B, these two flip-flop is giving you a state transition. Like let's say it was 0, 0 means state A, and you got a 1 in the current value. The next clock through this whole logic, this will switch to 0, 1. Like AT will stay at 0, but BT will switch to 1 because we are feeding in that logic from here. Look, see, the DB is basically X. So X was 1. So next clock cycle, your BT, this Q output will become 1, right? So you'll have this 0, 1 state on this fashion. So I recommend follow through this circuit and just put some cases like some sequence, small sequence 1 1 1 1 0 1 0 0 1 1 1 0, something like that, 3 4 like 10 cases probably as a sequence, and derived these logics and see at each clock how these Q values of the A and B are changing, so that you convince yourself this is the circuit you are looking for. Okay, an output equation AT, BT bar and X. So we don't need to have a complementary get here because Q bar is basically your BT bar. Is a inverse relation. So we can use that output of the B and ANDed with AT directly, which is like from the flip-flop A, and X, which comes from the primary input. That becomes your Z, and AT plus 1 is basically implementing your AT, BT, AT and BT. We are taking up them, ANDing them, and also AND BT with the X, then ORing them. That becomes your AT plus 1, and BT plus 1 we have just discussed, that is nothing but the X is directly fed into that flip-flop. So this is what the circuit would look like with the 2D flip-flop, couple of logics. You come up with this machine which can recognize a sequence 1 1 0 1.